CIS 3730, Logical Database Design. Through ER Model Transformation. A Database Design Lifecycle. Hi. Welcome to the third sessions on ER modeling. The first two sessions covered the user requirements analysis and conceptual ER modeling. This third session discusses the logical database design phase. The input to this phase is the conceptual ER model. The logical database design focuses on transform the conceptual ER model to a logical model for relational databases. The end product of this design phase is a logical ER model which is ready to be implemented in a database system. Learning objectives. This session will discuss the objectives of logical database design. Revisit the relational data model. Transform conceptual ER models into logical relational models. Convert unsupported types of attribute. Implement relationships using foreign keys. Discuss the best practice in ER model mapping. Logical database design bridges the gap. As discussed in earlier sessions, the database design methodology borrowed proven practice and techniques from other disciplines. Here is one such example. The automobile industry first visualizes a new car model in conceptual drawings to show their understanding of what drivers want in the future and new ideas. The industry uses it to get market feedback before investing on building the car. The targeted audience are customers. They then build a concept car model to show how the car could be built. The target audience is mainly engineers for them to figure out how to manufacture the car. The auto companies have followed this practice since the start of the automobile industry. The database design adapted a similar approach to create a conceptual data model to show to the business user our understanding of the user requirements and conceptual database to be built. The logical design is to transform the concept data model to a logical data model for implementing the database in the targeted database systems such as Oracle, which is what we will discuss in this session. Logical database design for relational database systems. In this approach, the logical database design transform a given conceptual ER model into a relational data model that can be created in a relational database such as Oracle, SQL Server, or MySQL. Interact with ChatGPT about the rationales for logical database design and explore logical design examples. Example prompts. I am learning database design in my college class. Could you explain the purpose for logical database design and why it is necessary? Could you please show me some examples of logical database design? Relational data model revisited. We will discuss the techniques and steps to transform a conceptual data model to a relational data model first. It is a good idea to refresh the concepts of relational data model first. A relation is like a table as shown in this student relation example. Each relation must have a unique name. Recall the error messages you might get when you try to run the table creation SQL script more than once. It is because the table has already been created and we cannot create another table with the same name. A relation may have multiple fields of specific data types like string or number. A relation must have a primary key, that is the unique identifier for each row in the table. If the key is a composite key, it must include a minimal set of fields. That is, satisfying the minimality rule. A field is a column in the table. Each row is usually called a record or an object instance. Each attribute value must be atomic, i.e., a simple and single attribute value. Relationships between tables are foreign keys. The concept of foreign keys is used to represent the relationship between two tables as shown in this diagram. A foreign key is the primary key field in another table to establish the connection between the tables. Note that both foreign key and primary key may be in the same table to create a recursive or unary relationship between itself. Gap analysis, ER modeling concepts. Before discussing the techniques used to transform conceptual data models, we want to know what ER modeling concepts are not supported by the relational data model. This table below shows all ER modeling concepts we have used to create conceptual data models. Gap analysis, relational model differences. The second column of the table showed the corresponding concepts of the relational data model that are equivalent to the ER modeling concepts in the first column. Note that they are equivalent and may not be identical. We will discuss how to handle the differences later. Those red crosses in the second column showed the ER concepts have no equivalent concepts in the relational data model. There are about half of the ER model concepts that need to be mapped to relational data model concepts. Those unsupported ER concepts can also explain why ER modeling is popular in database design. It is because the ER model offers a rich set of modeling vocabularies to allow data modelers to capture the data elements and business rules precisely and correctly in conceptual ER modeling. Logical database design roadmap. Start with deciding a good naming convention for relations and fields, followed by mapping normal entity types, and then map each type of attributes and each type of relationships. And finally, mapping supertype/subtype relationships. We will discuss the techniques in each step and refer to the techniques as mapping rules. Decide a naming convention based on the relational data model naming standard. Relational databases have specific naming standards. We should adopt the appropriate naming convention to avoid errors later when we implement the logical data model. That is, adapting a good naming standard now can help reduce redo work in the following design phases. The following are a general guideline for the naming convention in the best practice. Avoid reserved keywords. Choose simple descriptive names. In lower cases except in documentation for human readability. Use underscore as the separator for multiple word names. Avoid the space character because a space character requires to be enclosed by double quotes in SQL statements like academic advisor or unit price. Select the singular, not plural words for relation names such as student versus students, course versus courses, class versus classes. Keep foreign key names consistent with their referenced primary key names if possible. Establish a naming standard and enforce it. 1. Map each entity type to a relation table. This mapping step is straightforward. For each entity type, we create a corresponding table for it. If the primary key of each entity type should also be carried over to the map table. 2. Convert unsupported types of attributes. After entity types are mapped, we move to mapping attributes for each entity type as follows. Each single-valued and simple attribute such as the email attribute in this example should be directly mapped into a field in the student table. For each composite attribute, map each of its component attributes into a field in the table. For example, the composite name attribute is mapped into first name, mid-name initial, and last name fields. Another choice is to merge all components into a single field, for example, merging first name, mid-name initial and last name into a single field in the table. The main difference between creating separate fields and merging it into a single field is that the separate fields allows to sort the data by each component field like sorting all students by their last name. But, merging them into a single field would lose such a flexibility. In this example, we chose to keep all leaf attributes, mark the leaves, to allow us to sort students by either first, middle, or last name in database query. In contrast, if we merge them into a single name string, we would use pattern match in SQL queries to sort by different part of the student name, which is complex to get the correct sorting. Each multivalued attribute is always mapped into a separate table. For example, the multivalued attribute phone number is mapped into a new table called student phone. It starts with an attribute, phone. Each new table must have a primary key. Since a student may have multiple phone numbers, the foreign key ID student ID can't uniquely identify each phone number in the new table. So, we create a surrogate key as the unique identifier for each new table as shown in this example. We then insert the primary key of the student table into the new tables, student location and student phone as foreign keys to establish the relationships back to the student. Those new relationships are one-to-many relationships with the mandatory participations by assuming that location and phone number are required attributes in the conceptual ER model. Each computing attribute is not mapped to a stored field. Instead, its calculation is written down in the design document and the user guide later to compute the GPA information. So, those 4 steps showed the techniques, i.e., the mapping rules to transform each attribute type in the conceptual ER model. 3. Map binary one-to-one relationships. After all entity types and attributes are mapped, we are ready to map relationships. Generally, all relationships in an ER model are implemented as foreign keys in the relational data model. Hence, we will focus on where to insert foreign keys. We begin with the simplest relationship, the one-to-one, binary relationships. The mapping example is the relationship between employee and office. This example assumed 2 business rules. 1. Each employee is always assigned one and only one office. Both its minimal and maximum cardinalities are 1. The second rule is that an office is occupied by only one employee. So, its maximum cardinality is 1. But, an office may not be occupied by anyone. Hence, its minimal cardinality is 0. To implement the one-to-one relationship, we have 2 scenarios. The first scenario is that only one of the entity types has the mandatory participation. In this case, that entity type is selected to add the foreign key referencing to the primary key of another entity type. In this example, employee has the mandatory participation, the foreign key, office ID is inserted into it to reference to office's primary key. The second scenario is that both entity types have mandatory participation or both have optional participation. In this case, the primary key of either one can be inserted into another entity type as the foreign key. You might ask why it matters to select the entity type with the mandatory participation. The design choice is to reduce unnecessary nulls, blanks, in the foreign key field. For example, let's assume that we have 100 offices and only 50 employees. In our mapping, all office ID foreign keys in the employee table have values because every employee has an office. However, if we inserted the employee ID into office as a foreign key, we would have 50 blank instructor IDs, i.e., 50 null values, in the office table because only a half of the offices would have occupants. It is the reason that this mapping rule always selects the entity type with the mandatory participation to implement the relationship, i.e., to insert the foreign key. This example showed one of the very important guiding principles in the logical database design, to reduce null values. 4. Map binary one-to-many relationships. Next, we take on one-to-many relationships. We use the relationship between department and employee as an example. This example assumed 2 business rules. A department may hire 0 or many employees, but an employee works for only one department. The entity type with maximum cardinality of 1 should be used to implement the relationship, i.e., insert the foreign key. In our example, employee has the maximum cardinality of 1. The primary key of department is inserted into employee as the foreign key, department ID, that references back to the primary key. The mapping rules considered the second guiding principle. Conceptual data model mapping should avoid introducing unnecessary data redundancy. Let's explain this design principle in the next slide. Does it matter which side of a one-to-many relationship to choose? Let's illustrate how the mapping rules given in the previous slide work by looking ahead when the database is created. As shown in this example, we created those 2 tables, employee and department, containing some sample data. Following the mapping rules, department ID was inserted into employee as the foreign key referencing to the primary key of department. The mapping introduced a new foreign key field department ID in the employee table. Since each employee must work for one and only one department, we can insert their department ID into the foreign key field. The foreign key field department ID in the employee is redundant because the foreign key values replicated the primary key department IDs. We argue that redundancy is necessary because the foreign key department ID is the only way to implement the relationship between department and employee. We have no other choice. Hence, the second guiding principle is obeyed. But, what would happen in the database if we did not follow the mapping rules? Instead, we introduced the foreign key, employee ID, in department to reference to the primary key of employee. In this incorrect mapping, a new foreign key field, employee ID, would be added to the department table. Because a department may have multiple employees, we would have to replicate the department fields for each employee working for that department. We can see immediately that this practice would introduce redundant department data including department name and other fields, and those replicate field data are resulted from the incorrect implementation of the relationship. Hence, the redundancy can be avoided. As we discussed in the relation normalization, redundant data would cause update anomalies and result in non-normalized relations. Therefore, we should avoid such unwanted consequences as the best of our ability. 5. Map binary many-to-many relationships. We use the relationship between sales rep and customer as an example. This example assumed two business rules. First, a sales rep may have no customer or may have many customers. The second rule stated that a customer has at least one sales rep and may have multiple sales reps. Each many-to-many relationship is always transformed to a new relationship table, i.e., an association entity type. In our example, the relationship is mapped into a separate table, client relationship. We change the table name to a noun by following the best practice. We create a surrogate key as the primary key of the new table. We then insert the primary key of sales rep and the primary key of customer to the new table as foreign keys. Finally, replace the M2M relationship with two 1-to-M relationships linking the new association entity type back to sales rep and customer, respectively. Note that the cardinalities of the new association entity type to sales rep and customer must be one with the mandatory participation. The cardinalities from sales rep and customer to the new entity type are the same ones with each other before the mapping. 6. Map binary association entity type. The mapping example is the advisory association entity type between advisor and student. The first rule is to create a surrogate key to the association entity type. Recall in the discussion of the conceptual ER modeling. Associate entity types are not required to have primary keys. If the association entity type has already have a primary key, the surrogate key is not needed. The second mapping rule is to insert the primary keys of advisor and student as foreign keys into the association entity type. Map ternary association entity types. Mapping ternary association entity types is very similar to mapping binary association entity type. As shown in the example is the relationship between car, sales rep, and customer. This example assumed three business rules. First, a car may not be sold or sold to only one customer. Second, a sales per rep may not sell any car or may sell many cars. Third, a customer may not buy any car or may buy multiple cars. The first mapping rule is to create a surrogate key for ternary association entity type if it has no primary key. The second rule is inserting the primary keys of sales rep, car, and customer into the association entity type as foreign keys, respectively. 7. One-to-many unary relationships can be mapped as one-to-M binary relationships. As discussed in the ER conceptual modeling, a unary relationship is essentially a binary relationship in which the two participants are the same entity type, that is, a recursive relationship. Hence, a unary relationship can be mapped as a binary relationship using the mapping rules we discussed earlier. Let's see how those rules can be applied to unary relationships. First, let's start with one-to-many unary relationship as the employee supervising relationship example shown in this slide. This example assumed the business rules that an employee may manage no employees and may manage multiple employees, and an employee must report to one and only one manager. We directly apply the mapping rules for the binary one-to-many relationships by inserting the primary key employee ID into the same table as a foreign key, manager employee ID. Since both primary key and foreign key are in the same table, we must rename the foreign key to avoid field name conflict. 8. Many-to-many unary relationships can be mapped as many-to-many binary relationships. A many-to-many unary relation can be mapped using the same rules for the binary many-to-many relationships. The example used to show the mapping is the course prerequisite relationship. A course may not be a prerequisite for any other course or may be a prerequisite for multiple courses. On the other hand, a course may have no prerequisite or may have multiple prerequisites. Recall that we converted a binary many-to-many relationship to a new association entity type. We followed the same mapping rules to convert the unary relationship into the association entity type prerequisite and create the surrogate key prerequisite ID for the new entity type. Since both participants of the unary relationship is the same entity type course, the primary key is inserted into the association entity type twice and renamed one of the foreign keys to prerequisite course number. That is, those two foreign keys establish the relationship between a course and its prerequisite course. Finally, we created two one-to-many relationships to connect the new entity type to course indicating the prerequisite relationship. 9. Identifying relationships for weak entity types are mapped as one-to-many relationships. The identifying relationship between a weak entity type and the entity type it depends on is mapped using the same rules for mapping binary one-to-many relationships. As shown in this example, the academic program depends on the department offering the program. Following the mapping rules for binary one-to-many relationships, we insert the primary key of the department entity type to the weak entity type program as a foreign key. 10. Select which supertypes to keep and which ones to drop. The last type of relationships is the supertype/subtype relationships, i.e., the superclass/subclass relationships in Java or Python. The relationships can be mapped in multiple ways. We are going to show one of possible ways to map the relationships. The example used here is a person-entity type hierarchy. Person is the supertype of student and staff. Student in turn has two subtype entity types, undergraduate student and graduate student. Staff in turn has only one subtype entity type, faculty. The consideration for mapping the hierarchy is to reduce the number of resulted tables. Hence, first, we need to decide which supertypes to be mapped and which ones are dropped. If a supertype is dropped, its attributes should be added to all its subtypes, i.e., manually performing the inheritance for each subtype entity types. Let's assume that we decided to drop the supertypes person and student. It is because a school should usually have undergraduate students, graduate students, staff, and faculty members. The next step is to inherit all attributes of dropped supertype entity types to their subtype entity types. In this example, we manually copied ID, name, address, and phone number, major, and GPA to both undergraduate student and graduate student, and copied ID, name, address, and phone number to the staff entity type. Finally, implement the remaining supertype/subtype relationships as binary one-to-one relationships by inserting the primary key of the supertype into the subtype entity types as foreign keys. In this example, only one supertype/subtype relationship remained between staff and faculty. This relationship is mapped by inserting the primary key of staff, renamed as employee ID, into the subtype entity faculty as the foreign key referencing back to staff. Finally, rename field names as needed. In this example, we renamed the primary key field, ID of undergraduate and graduate, to student ID. Now we completed the mapping of the supertype/subtype hierarchy following those two mapping rules. Note that what we described in this slide is only one of possible ways to map supertype/subtype relationships. You may decide which approach is appropriate for a given type hierarchy and follow similar mapping rules. Interact with ChatGPT for common mistakes in logical database design. Example prompts. I am learning database design in my college class. Could you show me the common mistakes in the logical database design and use some examples to help me understand? Could you offer some key points I should keep in mind when working on logical database design? University database example, logical design. Here is the logical model transformed from the conceptual ER model of the university database design example. This example decided to drop all supertypes. The different approach to map the conceptual ER model of the university database design example. In this approach, the supertype person is retained and the supertype/subtype relationships are implemented by inserting the primary key of person into advisor, student, and instructor as foreign keys. Note that the foreign keys are renamed in the subtypes for readability. Mapping summary. The table summarizes the mapping rules discussed in transforming a conceptual ER model into a logical relational data model for easy reference. Salesforce's data model extends tables to objects and FCase relationships. The relational data model is only one of the choices for mapping a conceptual ER model. In this class, we selected the Salesforce's data model as an example of alternative data model for logical database design. For those who are not familiar with Salesforce, Salesforce is a cloud-based customer relationship management, CRM for short, software. It also provides a platform as a service to develop CRM applications on the Salesforce platform. The Salesforce's data model extended the relational data model to the concept of objects. The relationships in a conceptual ER model can be directly implemented as relationships between objects instead of using foreign keys. It also provided a rich set of attribute data types beyond those available in the relational databases. We will discuss those differences in detail in the next sessions. For now, the table highlighted the concepts of the Salesforce's data model to the ER modeling concepts. As shown in the table, all foreign keys were replaced by truly relationships. Logical design should follow the best practice. The guiding principles for transforming a conceptual ER model into a logical data model are summarized below. Completeness. All information captured in the conceptual ER model must be found in the mapped logical model. Correctness. All business rules are correctly retained and implemented. Minimalized data redundancy. Should not introduce unnecessary data redundancy. Null values should be kept as few as possible. Reduced fragmentation. Should avoid creating unnecessary new entity types, tables/objects, as we discussed in mapping supertype/subtype hierarchies. Interact with ChatGPT to understand why businesses are still using relational databases. Example prompts. Thank you for helping me study logical database design. Since the conceptual modeling is object-oriented, would object-oriented databases be a better choice than relational databases because it could eliminate the needs for mapping from a conceptual model to a relational model? Why there isn't any object-oriented database commonly used by Main Street businesses today? Summary. Mapping rules are discussed based on the best practices. There are exceptions to the practice. Using data integrity as the guiding principle. Suggested order of mappings. First, entity types and attributes. Second, supertype/subtype is a relationships. Third, unary and binary relationships. Fourth, ternary and higher degree relationships. Fifth, weak entities and weak relationships. The mapping process is a multi-step, iterative process. With that, it concludes this session on logical database design. Thank you for watching the video.